Assalamu alaikum wa rahmatullah wa barakatuh. Today our meeting about magnetic resonance imaging. We will talk in this session about magnetic resonance imaging physics. We will try to talk simply and try to give you some important informations for doctors or technicians or physicists or for anyone intends to pass the exam of International Medical Physics certified board. Magnetic resonance imaging. I know very well that magnetic resonance imaging is hard to understand, and all of us reading a lot of books trying to understand. But I think that all of us is feeling some confusion about physics. So we will try today, step by step, to talk together about MRI physics. But at first, I want to inform you the references, books. You can use it and you can read it easily, and you can download it from internet, like Magnetic Resonance Imaging Physical and Biological Principle book, or FRCR Physics Notes. Simple notes. You can use it if you are a doctor. If you want a lot of details, you can read this book about magnetic resonance imaging, physical and biological principle for Stewart. And for myself, I prefer to read Sproul, a book about magnetic resonance imaging principles, methods, and techniques. I am Islam Kamal. I'm a PhD in medical physics. I'll try to give you some information about magnetic resonance imaging. If you need to more clearance or to understand more and more, you have to contact with me or leave a message, and I'll be in contact with you anytime. Okay. So our outline today, we will talk about MRI machines, introduction to MRI, what's the meaning of T1 and T2 signal, what's spin echo sequence, what's the difference between T1, T2 and the proton density weighted imaging, what's the meaning of spatial encoding, slice selection, frequency encoding, phase encoding, what's the meaning of k-space, sequences, and so on. But mainly I want you to start with me step by step, and it's important today to clarify MRI, what's the components of MRI machine, and to know some basics about the basic idea of imaging in MRI. Okay, if we talk about MRI machines, we will find that there are two types of MRI machines. One of them is closed MRI and another one is open MRI. But if we talk simply about the components of MRI, we'll find that the MRI system is composed of main magnet, okay, and you'll find gradient coils, okay, and gradient power supply and radio frequency transmitters. Each component of MRI machine has a function, okay, but we will not talk deeply about the function of each component now, but during our explanation for MRI physics, I'll try to explain each component deeply and try to give you some details about the function of it. So I want you to understand something, that here there is a magnet, okay, closed MRI. You will find the patient here inside the magnet. I want you to know the axis of patients. The axis of patients. Axis of patients means that this patient placed here is placing in spine position in MRI, closed MRI, and this direction of patient is called z-axis, and you will find to another position. One of them is vertical to the patient, which is y-axis, and another one is horizontal to the patient, okay, is called x-axis. So I have three axes of patients. One of them is Z, which is longitudinal, okay, along the patient. As you see here, Z is Z direction, and this is our patient. And another axis, x-axis, and another one is vertical to the patient's y-axis. So I have here three axes of any MRI machine. That's very important to know this axis now. And later on I'll explain why I want you to understand this axis very well. Okay, so now we'll come back again for components of MRI machines. Here I'll find the components of MRI machines that I found. Magnet. This magnet, the main function of magnet is producing the magnetic field or the main magnetic field. When I'm talking about the main magnetic resonance imaging, so I have to use magnetic field. And I'll find gradient coil. Gradient coil have an important function in MRI imaging. I'll talk about it later. And radiofrequency coil. Okay, so radiofrequency coil is responsible for transmitting signal and receiving signal, transmitting pulse and receiving pulse. Transmitting type of electromagnetic waves is called radiofrequency pulse, and receiving it. So radiofrequency coil is specific for the body organ. When I use coil for imaging of brain, I use another coil when I use it for imaging of lumbar spine or ankle or knee. So there are different coils, different radio frequency coil. Each one is specific for the body organ I want to scan. Okay, but gradient coil is embedded in the main magnet. Okay, it's present in the main magnet. This gradient coil, I have three gradient coils. I have the three gradient coil. Come back to my image again here. This gradient coil. Okay, I have three gradient coil in different direction, X and Y and Z. So I have three gradient coil in Y direction, X direction, Z direction. Okay, later on I'll talk about the function of it, not now. But now I have a main magnet, gradient coil, radio frequency coil. Radio frequency coil is responsible for receiving and transmitting radio frequency pulse, and the gradient coil have a very important function, but I'll not talk about it now. Main magnet, which is responsible for producing the main magnetic field, which is affecting on the body or of patient body. Okay, so now I have another expression which is called Sham coil. Sham coil is using for uniformity of magnetic field. This magnetic field has lines of magnetic field at a certain value. So I want to check if the values of magnetic field is constant along the patient. So I'm using Sham coil for calibration and to check the uniformity of magnetic field along the patient. Okay, here I'll show for you some different types of radio frequency coil. As I said before, that there are different types of coil specific for different body organs. Okay, here for brain, here another coil for knee, another coil for, here's dorsal coil, flexible one, here for shoulder joints, another coil for wrist, and so on. We'll find some surface coil, and there are different coils. Each one is specific for specific organ. Okay, these coils are responsible for receiving and transmitting radio frequency pulse. So now I'll talk about the main idea of magnetic resonance imaging. The main idea of magnetic resonance imaging is transmitting radio frequency pulse, and radio frequency is a type of electromagnetic waves. Okay, this radio frequency pulse, like sine wave, transmitting it using coil, and our body here or receiving this radio frequency pulse. After certain time, the radio frequency pulse come back again to the receiver coil. I receive this radio frequency pulse. So now, again, this is the main magnet, two poles of the main magnet, north and south. Okay, and here I have this coil transmitting radio frequency pulse, causing excitation inside the patient body. After I switch off the radio frequency pulse or the transmitted pulse, the body will relax when the body relax or body tissue relax, the radio frequency pulse emission happen and receive this, and we are using a coil to receive this radio frequency pulse again. After that, we will translate this radio frequency pulse to image. Like here, this is our body tissue, okay? Receive, we have here a sensitive atoms or a sensitive molecule inside our body, receiving the radio frequency pulse coming from outside. And when I switch off this radio frequency pulse, the tissue emit the signal again, and the machine itself using this signal to translate it to image. Okay, so now I need a source of radio frequency pulse, which is our coil. I told you about it before. So the source of radio frequency pulse will be the coil, and we need a receiver for the signal coming out from the tissue, which is the radiofrequency coil. Okay, so I have now receiver and transmitter. Let us talking about the tissue itself. The tissue itself, which is receiving the radio frequency pulse coming from the coil. Which part of the tissue inside our body is receiving this pulse? Which molecule, which atom is receiving the radio frequency pulse? So I need an atom, a sensitive atom to the radio frequency pulse. I need a sensitive atom to the external magnetic field. Oh yeah, so I'll look for atom to be sensitive with the radio frequency pulse coming from outside. Okay, our scientists looking for the magnetic properties of nuclei, they found that hydrogen atoms, which has odd mass number, okay, has this hydrogen atom, its proton inside the magnetic atom, inside the hydrogen atom. So the proton inside any nucleus is composed of protons and neutrons. Okay, so the mass number in hydrogen atom is odd mass number, not even. Is odd mass number, not even. So the odd property of mass number giving a magnetic property for the hydrogen atom. So the hydrogen atom is highly sensitive to the magnetic field. Is highly sensitive to the magnetic field due to its odd mass number. But carbon and oxygen has even mass numbers. So they are non-magnetic. They have no magnetic property because they have even mass number. So odd mass number of atoms causing the magnetic property of this atom. Okay, so hydrogen atom is highly sensitive atom to the external magnetic field. Here I'll find that this is the proton which is inside the hydrogen atom, like this pole. This proton has a positive charge, spin around itself, as you see. So now this proton has a positive charge, so this is electric charge is moving now, moving in a path, so inducing of magnetic field. Any charge moving, okay, causing magnetic field. So now this charge which is moving in this path, okay, in a circular path here, spin around itself, causing magnetic field. So this is a magnetic field. Now it's like small magnet. So our proton here, so the proton here inside the hydrogen atom, it's like small magnet. So now it is sensitive to external magnetic field. So any magnetic fields coming from outside affecting on this proton, So now I find that the hydrogen atom has a higher sensitivity, 1, and so on. Fluorine is 0.08, sodium 23 is 0.09, phosphorus 0.06. So there are different sensitivity of different protons inside different atoms. So now this sensitivity is related to the protons inside different atoms. Okay, so now the imaging in magnetic resonance imaging depends on protons inside the hydrogen atom. Why? Because the protons inside the hydrogen atom is highly sensitive to the magnetic fields. Why when I ask myself now, why you need a hydrogen atom or the protons to be highly sensitive to magnetic field? Because if the protons are sensitive to the high magnetic field, now I can use this external magnetic field to give energy, to give radio frequency pulse, to move it from relaxation state to excited state. Okay, but in different atoms which are not sensitive to the external magnetic field, so I can't excite it because the atoms are not sensitive to the magnetic field. Okay, so the sensitivity of the protons inside the atom is a very important very important property. Okay, now we'll talk another property is called precision of the protons. These protons inside the hydrogen atom has a motion of spin. Okay, when I apply external magnetic field, now this proton inside our bodies, okay, the proton, we have million of protons, okay, inside our bodies. These protons moving, spin around its own axis. Okay, the protons spin around its own axis. This is in random distribution. These protons inside our body in random distribution. Someone ask himself, so now I have a lot of tiny magnets inside my body. Okay, but the net magnetization of all these protons is 0. Why? Because you will find that a certain magnet or a certain proton is directed towards a direction, you will find another proton towards another direction. So all of them, you will find two protons or two magnetic force, okay, in opposite directions, so neglect each other. So the net magnetization will be 0. This is in normal state without applying the external magnetic field. So now I'm trying to explain to you that the protons in a free state without external magnetic field inside our bodies will be like this. You will find the proton here towards a certain direction, you will find another one in opposite direction. So the net magnetization of protons inside our bodies without this external magnetic field will be 0. But the proton here has spin motion. When applying the external magnetic field, what will happen to the proton? The protons, which is of hydrogen atoms, the proton now of hydrogen atom are highly sensitive to the external magnetic field, will align themselves with the lines of external magnetic field. You will find that protons align up and another protons align down. Align up with the same direction of magnetic field, okay, from south to north, and another protons will align down, okay. And the protons, we said before that the proton now has a spin motion. After applying the external magnetic field, first you will find that protons will align with the external magnetic field. Second, the proton acquire another motion, which is called precision motion. As you see here, this proton spin around itself, okay, at the same time spin around this axis. This axis is the axis of external magnetic field. This is the line of magnetic field, of external magnetic field. So this motion is called precision. Here, after applying the external magnetic field, the proton here spin around itself at the same time acquires a precession motion. This precession has a frequency. This precession motion has a frequency which is related to the magnetic force of the external magnetic field. When we apply the patient, when we apply 1.5 Tesla, that causing precession frequency, okay, not like 0.5 Tesla. Different magnetic fields, different force of magnetic field causing different precession frequency according to Larmor equation. Here in no external magnetic field, here after applying external magnetic field, some moving up, some moving down. Here you will find after applying the external magnetic field, you will find the protons, okay, start to precess, as you see, start to precess. But the proton precess here, some protons moving up or towards up or stands up, and another proton down. And the protons, all of them precess with the same frequency. All of them precess with the same frequency, but in different phase. You'll find here the proton, not all of them moving in the same phase, no, with different phase. So after applying the external magnetic field, protons align themselves with the line of the magnetic field, and some protons aligned up and another protons aligned down, okay, and the proton acquire precess motion. This is the frequency of precess. The frequency of precession depends on the external magnetic field, okay, as you see here the external magnetic field, and we represent the proton with this red arrow, okay, and now the proton precess around the external magnetic field. The precession frequency depends on external magnetic force. Here again, this frequency of precession is called Larmor frequency. Why? Larmor frequency, which is related to Larmor equation. I want to give you the info. Yes, this one. Okay, here this is the Larmor frequency, which is the angular frequency. Okay, if I want to calculate the frequency of protons, the frequency of precession, okay, from this equation, which is equal to the gyromagnetic ratio, which is specific for the atom itself, which proton, which type of proton of hydrogen or proton of fluorine or proton of phosphorus, and so on. And this is the external magnetic field. So the gyromagnetic ratio is constant, but the external magnetic field, which is represented by B naught, is not constant. It is related to the machine itself. When applying 1 Tesla machine, causing angular frequency is around 42 megahertz. Okay, when applying 1 Tesla, 42 megahertz. Okay, but with fluorine, the precession frequency or Larmor frequency of protons inside the protons will be 40 megahertz, and for phosphorus 17, and sodium according to the sensitivity. The proton of hydrogen atom, which has no neutrons, only protons, odd number of protons, highly sensitive, so the precession frequency, so the protons of hydrogen atom will be highly sensitive to the external magnetic field, which is 1 Tesla. So the Larmor frequency of protons of hydrogen atom, higher value, which is 42.5 megahertz. Okay, so here when I apply 1 Tesla, so the Larmor frequency will be 42.5. When I applying 1.5 Tesla, the Larmor frequency will be higher, and 3 Tesla, the Larmor frequency will be higher, okay, and so on. Increasing the external magnetic field from this equation will causing higher Larmor frequency. So what's next? What's after applying the protons or the body of patient inside the external magnetic field? Here I applying the patient inside the external magnetic field, okay. As I said before, that some protons are lined up and another proton are lined down. The protons are lined up in relaxation state. like people moving on their feet. So they are in relaxation state. But protons are lying down, that you'll find this proton in excited state. Exert a lot of effort to be in this state. So these protons in excited state. But the protons aligned with the lines of external magnetic field, okay, will be more aligned up, will be in relaxation state. The number of protons which is aligning up, the difference between the number of protons which is aligned up and aligned down per million of protons will be 7 protons. If I have 1,000,007 protons aligned up, I'll find 1,000,000, only 1,000,000 protons aligned down. Okay, so for each 1,000,007 protons aligned up, I'll find 1,000,000 of protons aligned down. So, as I said before, that each proton aligned up, I'll find another proton aligned down. So, two opposite magnetic force neglect each other. So now, this is the axis of patient, z-axis, and y-axis, x-axis, as I explained before to you. Here, each arrow representing the number of protons. So I have, after applying the external magnetic field, I'll find that a number of protons aligned up and a number of protons aligned down. Okay, so each proton aligned up has another proton aligned down. Okay, so this proton will neglect the opposite one, and so on. So the net result of, after neglecting the magnetic force, okay, will be certain number of protons aligned in the z direction, which is the direction of patient, which is the axis of patient, which is the axis of the main magnetic field, or which is the axis of the main magnetic field. So finally I'll find some protons aligned up, okay, aligned up with the main magnetic field, or with the main line of magnetic field in the z direction. Here, these protons in certain direction, I'll find another proton in other direction. Okay, two opposite force neglect each other, so the result force okay, and so on. Okay, so now I have some protons aligned up in the z direction. This proton is aligned, the protons here are aligned with the main magnetic fields. Okay, these protons, each one has a certain magnetic moment. Each one has a certain magnetic moment. So the protons here in z direction adding and increasing the magnetic force in the z direction. But how can I discriminate between the magnetic moment or the magnetic force coming from the protons and the magnetic or the magnetization coming from the main magnetic field? It's impossible to discriminate between the two magnetization. The magnetization caused by the proton itself and the magnetization caused by the main magnetic field. So if I want to detect the magnetization of protons itself, I have to do another thing. I have to do something to move these protons in another direction. Now this proton in z direction. So I want to detect, if I get here a receiver, okay, radiofrequency coil, to receive the signal coming out from this magnetization, because these protons which is moving in z direction and moving in a coil, okay, this coil will induce current in this coil. But this current is my signal. The current coming out from this magnetization, which is the summation of proton itself and the main magnetic field, I can discriminate between it. So I want to detect only the current or the signal coming out from the proton itself, not from the protons and the main magnetic field which is in the z direction. How can I do this? So I have to give the proton some energy to be in the excited state. Now the proton in the relaxation state with the main field. If I give radio frequency pulse, this pulse causing the protons to be excited in another direction, like XY direction. After that, if I want to detect the signal coming out from the proton in XY direction, so the signal here will be only coming out from the proton itself. Okay, it's a very important point to know why we can't detect the signal coming out from the proton. The proton here is a magnetic field moving, causing adding or causing increasing the main magnetic field. When I use a radio frequency coil, so this is a magnetic field inside, inducing the magnetic field inside coil, inducing current. This current is my signal, which I use it to form the image finally. So if I want to discriminate between the signal coming out from the protons and the main magnetic field, I have to give some energy to the protons to be in another direction. After that, if I want to detect the signal coming out from the proton, it will be easy, because the proton will induce a signal in XY direction, not in Z direction. So how can I give the energy to the radio frequency proton, to the protons? If we come back to the Larmor equation, Larmor equation define to us how can I calculate the Larmor frequency. Larmor frequency means the precession frequency of protons which are exposed to the external magnetic field. If I know the frequency of protons, so it's easy to give external energy, external radio frequency pulse with a frequency, with the same frequency of protons frequency. Like this example, if I have two cars moving with the same speed, so it's easy for this driver to transfer energy to another driver to transfer this sandwich. But if the two drivers moving with different speed, so it's very hard to transfer energy between. So it's important to know the frequency of protons by Larmor equations according to knowing the external magnetic field, because gyromagnetic ratio is constant, specific for each atom. Now if I know which type of machine, 1.5 Tesla or 1 Tesla or 0.5 Tesla, also it's easy to know the Larmor frequency or the precession frequency of protons. So it's easy to create a radio frequency pulse coming from the coil to excite the protons with frequency which is equal to the Larmor frequency of protons. So like radio waves, as you see there are different radio frequency, but when we are using tuning property in the radio, okay, to adjust the channel of radio at a specific frequency to acquire the frequency from outside, the same idea. So now here, after applying the radio frequency pulse coming from outside, all these protons were in Z direction, adding magnetic force to the Z direction. Yes, the net magnetization of protons and the main magnetic field will be this line. would be this arrow, which is longitudinal magnetization, which is called the longitudinal magnetization. So the protons, when we apply the patient, when we position the patient in supine position inside the magnetic field, the protons now align with the main magnetic field, okay, causing this longitudinal magnetization, okay. So the red arrow, this arrow is representing the magnetization in the z direction, which is called longitudinal magnetization. So now I know well the precision frequency of protons. After applying the radio frequency pulse coming from outside with the same frequency of protons, what will happen? The protons will acquire energy and will transfer to excited state. Will transfer to the excited state. And the longitudinal magnetization amount here or will decrease. And I'll find another magnetization vector appear in the XY direction, which is called transversal magnetization, because the protons here, some protons here acquire some energy, okay. Protons here acquire the radio frequency pulse and will be in the other direction or the excited state. And not only this, but another thing will be happen, which is the protons here are out of phase. You remember this image? Here, the protons here in normal state with applying the external magnetic field, the protons are out of phase, but all of them have the same precision frequency. After applying the radio frequency pulse, the protons will be in phase. You see that here the protons are dephased, not in phase, before applying the radio frequency pulse, but after applying the radio frequency pulse, all protons become in phase. And another magnetization will appear in the XY direction, which is called transversal magnetization. So now this transversal magnetization here moving in the XY direction with this arrow inside the coil, induce a signal, inducing current, using the receiving coil translate this current or translate this signal to image. Okay, so now I can discriminate between the magnetization coming out from proton itself and the magnetization coming out from the main magnet. Okay, so now I explained for you longitudinal magnetization, which is obvious for all of us in the direction before applying the radio frequency pulse, and the longitudinal magnetization here is due to the protons which are aligned in the direction of the main magnetic fields, and transversal magnetization which appear in the XY direction after applying the radio frequency pulse, which causing the protons to be in phase and in the excited state. This transversal magnetization will induce current in the receiver coil, as you see, using this current or using this signal to translate it to image. Now we'll talk about different meaning, which is called after we switch off the radio frequency pulse, what will be happening? Now we are trying to switch off the radio frequency pulse coming from outside. What will be happening? What we will know in the next video.